All right, good morning, everyone. Welcome back. Today we're going over 2D and 3D geometry. So we're going to very quickly review everything about right angle triangles. We'll do that in about 15 minutes. So that, is Pythagoras, and then the trigonometric ratios, SOHCAHTOA, area of a right angle triangle, etc. Then we're going to move on to non-right angle triangles. So we're going to talk about the general formula for the area of a triangle. We're going to talk about the sine rule and the cosine rule, as well as the ambiguous case of the sine rule. All right. After that, we're going to talk about a bunch of IB problems on that topic. And then we're going to do the 3D solids. So that's spheres and cones and cylinders and prisms, etc. So with that said, I'm going to share my screen and we will get started. So let's kick it off with something fairly basic. The area of a triangle, okay? If I know the base of a triangle and I know its height, then you can imagine constructing a rectangle with that same base and that same height. And what you'll notice is that whatever triangle you draw with a vertex along the top of that rectangle, the area of the triangle is going to be half the area of the total rectangle. And we know that a rectangle has an area of base times height or height times width, however you want to write it. So if the triangle is half of that, then the area of a triangle is going to be half of base times height. Okay, I'll give you 30 seconds to do this really quick example. So I have a triangle with area 4, so I can write, using the formula we just explained, area is half of base times height. And I see that the base is 2, so half times 2 times h is equal to 4, and the half and the 2 will cancel, and so we must have h is equal to 4. Pythagoras' theorem. This gives us a relation between the side lengths of a right angle triangle. If I have a triangle with a right angle between A and B, and the longest side called C, then A squared plus B squared is equal to C squared. This is not in your formula booklet because it's considered almost too elementary. And the only important thing to remember really about it is that C is the longest side. It's very common for students to make the mistake of trying to use A squared plus C squared equals B squared, and that's going to lead you to the wrong answer. So before you use Pythagoras, just make sure which side is C. C is the longest side, and we call it the hypotenuse. All right, let's do an example. If I have a right triangle, ABC, and I have AB equals BC equals 2. All right. If two sides are equal, then neither of them can be the longest side. So the longest side must be the side AC. And therefore, AC squared is going to be equal to AB squared plus BC squared, which is equal to 2 squared plus 2 squared, in other words, 8, which means that AC is equal to root 8. All right. Continuing. Another 30 seconds to do this example. I know it's very basic stuff, but I want to get through it, and then we'll have a solid foundation for the things that come after. All right, I'm going to go over the answer to this. The longest side here is 6, and so by Pythagoras, I can write 6 squared is equal to 5 squared plus x squared. So 36 is equal to 25 plus x squared, means that x squared is equal to 11, and that means that x is equal to root 11. Note that x is equal to negative root 11 is not a valid answer because a triangle can't have a negative side length. And so root 11 is my answer. All right, now the trigonometric ratios, SOHCAHTOA. All right, so when I have a right angle triangle with an angle theta, an acute angle theta, less than 90 degrees, then the trigonometric ratios sine, cos, and tan are defined by sine of theta is equal to opposite divided by hypotenuse. Cos of theta is equal to adjacent divided by hypotenuse, and tan of theta is opposite over adjacent. So basically, sine, cos, and tan are functions that will take in a specific angle and will tell us the ratio of some specific sides of the triangle, depending on whether you're using sine, cos, or tan. And notice that sine and cos are both related to the hypotenuse, and tan is the one that is not related to the hypotenuse. Now you can remember these by using the trick SOHCAHTOA, because I have sine for opposite over for O over H, so, ka for cosine of adjacent over hypotenuse, and toa for tan of opposite over adjacent. So SOHCAHTOA is a good mnemonic for remembering this. Okay, so let's do a quick example, and then I'll give you a chance to do a problem. I have a triangle with a hypotenuse 4 and an opposite side compared to this angle of, sorry, a hypotenuse of 5 and side length 4 opposite an angle theta. We need to know the adjacent and the hypotenuse. We know the hypotenuse is 5, and we don't know what the adjacent side is. We can find it using Pythagoras. If I do 5 squared is equal to 4 squared plus a squared, then I find 25 is equal to 16 plus a squared. A squared is equal to 9, and so a is equal to 3. And then cosine of theta is 3 over 5. Okay, I'm going to give you, let's say, 30 seconds for this example. All right, looks like most of you have got the right answer. So let's think about sine of theta. Sine, remember, I'm going to write SOHCAHTOA over here just for people to remember. Sine is the opposite over the adjacent. So the opposite side is 5, and the adjacent side is 4. Remember, the adjacent side is never the longest side. Sorry, it's opposite over hypotenuse. So over root 41. So sine is going to be 5 over root 41. That's this option here. Okay? Now for part B, I'm looking for the cosine of theta. And cosine, according to SOHCAHTOA, is adjacent over hypotenuse. And that is 4 over root 41. So that's option number 4. And finally, let's do the tan of theta. And tan of theta is opposite over adjacent. The opposite side is 5. And the adjacent side is the one that touches the angle that is not the hypotenuse, right? Because we know that this one is always going to be h. So the a is this, and therefore tan of theta is equal to 5 over 4. Another thing to know, the angles in a triangle add up to 180 degrees. It's a kind of very important rule that you'll need to remember for certain geometry problems, and it's going to make your life a lot simpler once you realize that, okay? All right, so if I know that all the angles in this triangle add up to 180 degrees, then I use the fact that the right angle is 90 degrees, and I write 90 degrees, I don't know what that is. I write 90 degrees plus 59 degrees plus theta is equal to 180 degrees. All right, I'm going to cancel 90 on both sides. 59 degrees plus theta is equal to 90, and therefore theta is equal to 90 minus 59, and that's 31 degrees. Okay, option 2. Okay, now, if we are trying to find angles in a right triangle, right, we know that sine theta, cos theta, or tan theta can be found using the ratios of sides in a right angled triangle. But we can also find theta using what we call an inverse trigonometric function on a calculator. So if I know what sine theta is, I can use the function inverse sine, or sine -1, to get back theta. I can use the function cos -1 to get theta from cos theta, and tan -1 to get theta from tan theta. And this applies whenever theta is less than 90 degrees. If it's not, then the sine is not going to be completely correct. Okay? But in any case, that's not going to apply because in a right angle triangle, if this angle is 90 degrees, then none of the other angles can be bigger than 90 degrees. So there's no issue. So in this example, I'm trying to find theta, and I'm given the triangle. It has a side length 4 opposite an angle theta, and it has a hypotenuse of 5. Okay, so the side length, I have compared to the angle, I have the opposite side and the hypotenuse side. So I can write sine of theta is equal to 4 over 5. And then I'm just going to quickly go to my calculator screen and show you the inverse sine and inverse cos and inverse tan functions are just above the sine, cos, and tan key. So you're going to go second sine 4 divided by 5. You're going to make sure, depending on the question, that your calculator is in the right mode. So I'm in radians right now. I need to be in degrees. And I hit enter, and I get 53.1 degrees. Okay, so let's go back and put that in. 53.1 degrees. It was an example. Okay, perfect. Next slide. We can also find side lengths from an angle if we're given a specific angle. So we can use the calculator to evaluate what sine cos of tan of a specific angle is. And I can use that then to solve for one unknown in a triangle side. So let's say I know that sine of 40 degrees, using my calculator, that's going to be 0.643. And that tells me what the opposite over the hypotenuse ratio is going to be. So concretely, I have a triangle now that has a hypotenuse of 5 centimeters and then a side length x opposite an angle of 35 degrees. Okay, so I have this opposite x and the hypotenuse 5. So I'm going to use sine of 35 degrees. And sine of 35 degrees should be equal to x over 5. And x is 5 sine 35. And if you punch that into your calculator, you'll get 2.87. And you just put centimeters because the hypotenuse is marked in centimeters. So I'm going to give you, let's say 30 seconds to do this. Okay, so this was a bit of a tricky one because there's also some difficult rounding happening here, but let's go over it. So find theta to the nearest degree. I know the side 5 and the side 6. Compared to theta, that is the adjacent side and the hypotenuse side. So cosine of theta is equal to 5 over 6. And so I'm going to go to my calculator and find the inverse cos of 5 over 6. Let me do that. So I'm going to just clear this. I'm going to go second inverse cos 5 divided by 6. Close my bracket, hit enter, and I get 33.557. But the question says to give the angle to the nearest degree. And the nearest degree, because I'm above 33.5, I have to round up to 34 degrees. So if you put 33, that was a deliberate trick. Let's go back and put in 34 degrees. And then we go to part B. And now we're trying to find the value of x, okay? When you are using an angle that you found to find something else in a subsequent part, it's always better to use the exact value of the angle that's stored in your calculator instead of using 34 degrees, because it's only an approximation. So this is approximately 34 degrees, but thankfully we have the exact angle stored in the calculator. So if I'm looking for x, then x is the opposite side, and I know I can either use tan or sine because both tan and sine involve the opposite. I think sine is a little bit easier, so I'm going to write sine of theta is equal to x over 6, and therefore x is equal to 6 sine of theta. And theta is the angle we just found, so if I go back to my calculator and I type in 6 times sine. And now what you're going to do to get that answer back, you can either scroll up and you can hit enter, or you can just use second and answer to substitute in the last value that your calculator spat out. And I'm going to get 3.31. Okay, so let's go back. And we found 3.3. All right, that was everything for the right angle triangles. I know that was kind of like basic review, things that you're mostly supposed to know before IB, but it's helpful just to set it up so that we can now talk about the more advanced stuff. So let's talk about the area of a non-right angle triangle. So we said earlier, right, that if I have the base of a triangle and its height, um, I can find its area just by doing half of base times height. But in general, I'm not going to know the height in triangles. It's much more common to know the side lengths, all right? But here's what I want you to notice. In this triangle with hypotenuse A and this length h and the angle c, h is opposite c and the hypotenuse is a. So sine of c is h divided by a, which means I can actually write the height of a right angle triangle, of a non-right angle triangle, as a times sine of c. And that's really helpful because then I can just use the formula that I have, which is area is equal to half base times height. If I plug that in, I get 1 over 2 AB sine C. And this is in your formula booklet. I'm only showing you this so you understand where it came from. But in general, you can just apply this formula when you know two sides and the angle between those two sides. That part's important. So if you are given two sides of a triangle and another side and another angle, or maybe both other angles, you first have to find the angle between the two sides. I'm begging you, don't use the angle that's not included to try and calculate the area. It's so common, but it's so easy of a mistake to rectify. Example. Triangle ABC has AB is equal to 5, BC is equal to 3, and C is equal to 35. All right, I don't know about you, but I don't like thinking about these without a picture. So I'm just going to draw. That's AB. They will say that that's BC. And we know that the angle at C, so this is A, B, C. Uh, the angle here, I haven't drawn it very well. This is supposed to be 35 degrees. Okay? And we're trying to find the area of the triangle. So this is that is length 3, and that is length 5. And I've actually done a whoopsie in this example. I'm supposed to be giving you the angle B, the angle that's between the two sides. Otherwise, this doesn't work. So we actually have the angle B between the two sides. The angle B between the two sides is 35 degrees, and therefore the area is half of 3 times 5 times sine of 35 degrees. And if you plug that into your calculator, you will find 4.30. All right. Next. So I'm going to give you maybe, let's say, 30 seconds to do this example. I have two sides and the angle between them, which means that the area I can write as half AB sine C, or in this case, half 11 times 9 times sine of theta. And that's supposed to be equal to 40. All right? So what I'm going to do, I'm going to bring this 1 over 2 to the right-hand side by multiplying by 2, and I'm going to get 80. And then 11 times 9 is 99, so I'm going to divide by 99, and that's going to give me sine of theta. And we don't actually have to use the calculator because we just want to find what sine of theta is, and we have done that. So 80 over 99, that's option 4. Next, let's talk about the sine rule. Okay, and the sine rule is actually a consequence of the rule that we just derived. And I'm going to show you that briefly for your own understanding. We know that the area is half AB sine C, okay? But that works for any two sides and the angle between them. So I could write AC sine B or BC sine A, and that would all work. So I can write all of these. It's just the half of the side lengths multiplied together, multiplied by the angle between them. And it doesn't matter which angle or two sides you pick. All right, and if I multiply everything here by 2, and then I divide by ABC, it's a bit of a weird, what's it called? Like manipulation. But the point is, if I just kind of do a bit of arithmetic, I end up with this formula. Sine of C over C is equal to sine of A over A is equal to sine of B over B. And that is one formulation of the sine law. The one that appears in your formula booklet is slightly different. They've just flipped the numerator and denominator, but they're actually the same thing. So they tell you that A over sine A is equal to B over sine B is equal to C over sine C. What does that mean as in words? It means that the ratio of a side length to the sine of the angle opposite it is always the same in a triangle. So in this example that I have here, 6 over sine of 70 is going to be the same as whatever this length is over the angle 41. Okay? So the ratio of the opposite side to the sine of the angle is a constant in every triangle. All right? And it's not the same constant necessarily in every triangle, but in a specific triangle, it has to be the same for any side and opposite angle that you pick. So let's do an example. I'm trying to find x in the triangle below. I know 6 and the opposite angle 70, so I can write 6 over sine of 70 degrees is equal to, I know that that's going to be equal to x over sine of c, because c is the angle opposite x. And that's a bit annoying because I don't know c, but I can find it out because the sum of angles in a triangle is 180. So if I do 180 minus 70 minus 41, I'm going to get 69. And therefore, I can write this as x over sine of 69 degrees. If I rearrange that, I'm going to get 6 sine of 69 degrees divided by sine of 70 degrees. And you can type that straight into your calculator, make sure you're in degrees, and you will get 5.96. for the length of x. Okay. Now I'm going to give you, 30 seconds to do this. All right, that's time. Let's go over this. So this is actually a little bit easier than the example we just did because I know 13. Oh, I know 13 and the opposite angle 80 degrees. So I can write 13 over sine of 80 degrees is equal to x over sine of 55 degrees. All right. And that means that x is going to be equal to 13 sine of 55 degrees over sine of 80 degrees. And if I plug that into my calculator, let me share my screen and show you that. So I have 13 times sine of, hang on, was it sine of 55 divided by sine of 80? Now I'm forgetting my steps. Yeah, sine of 55 divided by sine of 80. And that gives me 10.81. So let's put that in. 10.8. Nice. All right, I'm going to do our first exam style problem. This would be a pretty easy one on the exam, but it could theoretically show up. You're given the triangle ABC, and you're trying to find the length of AB. I'm going to give you, 3 minutes to try this on your own, and then we'll go over the solution. Okay, let's go over the solution here. This is a somewhat tricky question, and we're looking for the side length AB. I know already the two sides, 8 and 7, which are AC and BC in the larger triangle. But I don't know what AB is yet, all right? So I'm going to start by trying to find one of the angles in the triangle. I'm going to start by finding this angle. Because at least once I have an angle, then I'll be able to actually start to find things out about the larger triangle. Right now, I only know an angle for the smaller triangle, okay? So let's start with that. I'm going to find this angle using the sine rule in the smaller triangle. So I'm going to call this, let's call this D. Okay? And yeah, it's going to make our life easier. And then I can say that 6 over sine of B is equal to 7 over sine of 70 degrees. Or in other words, sine of B is equal to 6 over 7 sine of 70 degrees. Okay? Sine of 70 degrees. And if I actually calculate that on my TI-84, I'm going to get 0.805451. We'll just keep it exact for now. And then if I take the inverse sine of that, so I do sine negative 1, and that means that B is going to be equal to 53.65 degrees. I'm keeping it, more decimal places than I need for the moment. And then since this angle is 70 degrees, and this one is 53.65 degrees, then I can find the angle, the angle CDA, this angle over here, is 180 minus the angle 70 degrees, so this is 110 degrees. That's maybe a theorem that I didn't cover, so I'll just mention it quickly. When I have a straight line and an angle like this, if this has an angle theta, then that's 180 degrees minus theta. Okay, just something to bear in mind. And therefore that's 110 degrees. And then I can use 8 over sine of 110 degrees is equal to 6 over sine of A. I isolate sine of A. Sine of A is equal to 6 over 8 sine of 110 degrees. I put that into my calculator and I would get 0.704769. And then I take the inverse sine and I find A is equal to 44.81 degrees. Now, why did I find both of these? Because I'm looking for the side AB, which is opposite this angle here. So that's the angle that I would ideally like to know. And now I can find it by doing 180 degrees. Oops. 180 degrees minus 44.81 minus 53.65 degrees. And that will give me that C is equal to 81.54. Okay? And then I can use, maybe I should have done this after the, no, we can use the sine rule. That's fine. I'm gonna write one more time that 7 over, let's say, sine of A, so sine of 44.81 degrees is now going to be equal to AB over sine of the angle I just found there, which is sine of 81.54 degrees. And so AB is going to be equal to 7 sine 81.54 degrees over sine of 44.81 degrees. All right, I'm going to type that into my calculator just to verify. 81.54 gives me a sine of 0.989, and then I divide that by sine of that and multiply by 7, and I get 9.82. Now, in general, with these geometry problems, there's often a lot of ways you can solve the same question. And if you were to read the solution to this problem, you'll see that it actually uses the cosine rule, which is the rule we're about to talk about now in a second. The cosine rule. So this is a generalization of Pythagoras' theorem for the case of non-right-angled triangles. What does that mean exactly? Why is it a generalization? Well, if I draw a triangle like this, where the angle, this angle here is no longer a right angle, but now we'll just call it C. This is the side length C, A, and B. Then I have this formula, A squared plus B squared minus 2AB cosine of C is equal to C squared. Now, I say that it's a generalization of Pythagoras because when C is a right angle, so when C equals 90 degrees, we haven't covered the unit circle yet, but if you type it into your calculator, you will realize that cosine of 90 degrees is just 0. And so the formula becomes C squared is equal to A squared plus B squared. So this formula also works for the case of a right angle triangle because it depends on the angle, and it just is going to ignore the angle when it's 90 because it just makes a cosine of 0. Okay? So we use the cosine rule when we either know two sides and the angle between them, and we want to find a third side. So let's say I know I know A and B and C, and I'm trying to find the side C. Or I know all three sides, and I'm trying to find an angle by isolating cosine of C. Those are the two common cases that we do. So in this example, the question is giving us, let me just write everything out here. I'm going to say that this is A, B, and C. The question is saying that, or this example, I should say, is telling me that AB is equal to 3, BC is equal to 4, sorry, BC is over here. BC is equal to 4, and AC is equal to 5. So I haven't drawn this at all to scale. It's not an accurate triangle, but it doesn't matter. The longest side, sorry, not the longest side. We're going to use the side that's opposite the angle C, which is the length AB. The one that doesn't involve C is opposite C. So I write 3 squared is equal to 4 squared plus 5 squared minus 2 times 4 times 5 times cosine of C. And if I expand that out, I get this, okay? And if I isolate cosine C, I bring all the terms to one side. I'll bring these over there. That give me negative 32. And then I divide by, well, this is negative 40. So I get cosine of c is equal to 32 over 40. And then on my calculator, I do cos negative 1 of 32 over 40, and you'll find 36.9 degrees. Okay. I'm going to give you 30 seconds for this example. Okay, let's cover this. So I have a triangle, and I know two sides and the angle between them, and I'm looking for the opposite side. That's classic case of the cosine rule. I write x squared is equal to 13 squared plus 6 squared minus 2 times 6 times 13 cosine of 50 degrees. And all I'm going to do now is I'm actually just going to plug straight into my calculator. I'm going to say x is the square root. I'm not even going to bother doing any of the math because I could make a mistake. 13 squared plus 6 squared minus 2 times 6 times 13 cosine of 50 degrees. So let's put that straight into the calculator. I'll show you how. So I'm going to have here that. I'm going to go second, enter a square root. And I said I had 13 squared plus 6 squared minus 2 times 6 times 13 times cosine of 50 degrees. What do I get? I get 10.2. So let's go back. 10.2 is my answer. Now, IB style problem. So I'm going to give you guys 5 minutes to try this on your own, and then we'll go over the solution. All right, I think I'm going to go over the solution here. And even though we haven't actually covered it in the session yet, I just realized you're going to need to use the identity sine squared theta plus cos squared theta is equal to 1 here. So I'm sorry, maybe I should have done this problem a little bit later, but we can do most of it still. I'm given, hang on one second, I'm just going to reset the screen share so my iPad works. I'm given that cosine of r, which is this angle here, it's the angle between PR and QR, that's the cosine of that is negative 1 over 4, which tells me or suggests to me that I should probably use the cosine rule. And the cosine rule in this triangle says that 2 squared, the side opposite that angle, is equal to 3x over 2 squared plus x squared minus 2 times 3 over 2 x times cosine of r. If I write that out, that's 4 is equal to 9x squared over 4 plus x squared minus 2 times 3 over 2, which is 3, so 3x squared. And then cosine r, the question tells us, is minus 1 over 4. All right, so what do I get here? I get, if I do 9 plus 4, sorry, 9 over 4 plus 1 is 9 over 4 plus 4 over 4, so 13x squared over 4. And then I'm going to be adding plus another 3 over 4x squared. That's 4 is equal to 16x squared. Or in other words, 16 over 4. In other words, 16x squared is equal to 16, which means that x is equal to 1. Now, note, I took a square root, but I cannot write that x is equal to plus or minus 1 because x is a side length here. Sometimes, though, if the side length is labeled something like x plus 3, then x could be negative because x would not be a side length. But as soon as x is a side length, the side length can't be negative. So just check whatever solutions you get from doing these algebraic procedures, make sure that they don't invalidate the triangle. They don't make one of the side lengths negative. There's usually a point just for doing that. All right, so now I know x, which means that this is 1, and this is 3 over 2. And now I'm trying to find the area of the triangle. And I have a formula from earlier, which is 1 over 2 AB sine of c. Okay? Or I could write this in this case as 1 over 2 times 3 over 2 times 1 times sine of r. And that's actually just going to be equal to 3 over 4 sine r. but I don't know what sine r is right now. The question only gives us cosine of r. Thankfully, though, I can actually find sine of r by using the fact that sin squared of r plus cos squared of r is equal to 1. We're going to talk more about this in the session on Friday about trig identities. But sin squared plus cos squared is equal to 1. And I can write that now using what I know about cos squared, that sin squared plus 1 over 16, because I square negative 1 over 4, and it just becomes 1 over 16, is equal to 1. And that means that sin squared r is equal to 15 over 16, because 1 is the same as 16 over 16. So this is 15 over 16. And therefore, sine of r is equal to root 15 over 4, because the square root of 16 is a perfect number. It's an integer. And so finally, I write the answer as 3 over 4 times that is 3 root 15 over 16. That is my answer. Okay, and let's check that off. 3 root 15 over 16. Very well done. Now I want to talk about something very tricky, which is the ambiguous case of the sine rule. All right, and this doesn't show up too often, but once in a while, every second year or something, or every second time zone, this does show up on the exam, so you need to be familiar with it. But basically, what you will realize, and we'll talk about this more when we talk about the unit circle on Friday, but sine of 180 degrees minus an angle is the same as sine of that angle. And you can check that with your calculator if you want. You can plug in any angle you want, and then plug in sine of 180 degrees minus that angle, and you'll get the same as sine of the angle. And therefore, if a given triangle has a specific value for sine of A, but we don't know whether it is acute or obtuse, then there are going to be two possible side lengths A. And in this triangle, I should have said sine C is the thing that's given. That would have been consistent with the diagram. And then there's going to be two possible side lengths for A. Okay, the side, yeah. All right. And let's look at what that would mean in a specific example. When I type sine negative 1 of x into the calculator, it's always going to return an acute angle. But to find the corresponding obtuse angle, we take 180 degrees minus sine negative 1 of x. And let me actually show you something on the calculator to help solidify this concept. I'm going to take an angle, say 40. Let's say sine of 40 degrees. Okay? I'm going to hit enter. And now I'm going to do 180 minus 40. That's 140. And if I take sine of that, I get the same thing. So notice that sine of 140 is the same as sine of 40. Okay? And when I take inverse sine of this number, I get 40, even though I put in 140 to get it. Because if both values go to the same answer, the calculator basically has to make a decision as to which one it's going to give back. And sine negative 1 is a function, and it has been defined by convention to return angles between negative 90 and 90. Okay? So you just have to be aware of the fact that the calculator is only going to give you the acute angle, and sometimes there is an obtuse angle that could also work in the triangle. Now, it's not always going to work, because sometimes the angle that you would find, the obtuse angle, is going to be too big for another angle that you know in the triangle, right? It might be that once you find this angle and you add it with another angle in the triangle, that's bigger than 180, which would make this impossible, okay? So let's say I have a triangle ABC. I have the angle A is equal to 30, and the sides BC equals 10, and AC is equal to 12. So I'm going to draw this on the diagram above. It's going to make things a bit easier. So let's say we have BC. I would have to change the diagram a little bit. So I'm just going to actually draw a new one. I have BC is equal to 10, and then I have AC. Ugh, stupid screen share. Sorry. And then I have so that's BC And I'll say that that is AC, which is going to be 12. So let's put this as ACB, or the other way around actually is going to be better. BCA, BC is equal to 10, and AC is equal to 12, okay? And we know that this angle up here is going to be, I didn't draw this very well, so this is not actually a helpful triangle. Give me a second. I'm going to draw this properly so that we can actually use the diagram to understand this. So I'm going to draw the side length AC here. This is AC. I'm going to draw the angle A like that. And I'm going to say that this is supposed to be, that's A. Let's say this is 12. Okay, perfect. Okay, this is going to work. And now I'm going to say that this is BC. So A, C, and B. And this side length is 10. And this is 30 degrees. This is better. So what I want you to realize is that the way I've drawn this triangle, I could also have drawn another line for BC that looks like this that also has length of 10. So I need to have the same length as that. So I'm going to do approximately that, okay? And the way I find that line, essentially, is by reflecting it in this perpendicular here. They're going to be symmetric about that. They're going to form, actually, an isosceles triangle around that point. But that isn't too important. The point is that when we use the sine rule, we're going to find the acute angle B. We're not going to find this acute angle, which we might call B prime, all right? And so we're going to need to remember that when we actually calculate the possible angles. So let's start with what I know. I can write, using the sine rule, that 10 over sine of 30 degrees is equal to 12 over sine of B. Okay, and if I isolate that, that means sine of B is equal to 0.6. Now, this is where the symmetry comes into play. If I type into my calculator sine -1 of 0.6, I'm going to get 36.9 degrees. But I could also get 180 degrees minus 36.9 is 143 degrees. They both have the same value of sine. Sine of 143 degrees is equal to sine of 37 degrees, and approximately 0.6. Okay. And it's because both of those have the same value of sine that I have to remember that the calculator giving me the acute angle might be hiding from me an obtuse angle that also works. So I check, I say, okay, the obtuse angle would be 180 minus 36.9, and that's 143. And then what you have to do is check if that 143 fits in the triangle. What does that mean? I have an angle of 30 so far, and if I do 30 degrees plus 143 degrees, that's 173 degrees, which is still less than the maximum of a triangle, okay? If I had something that was 180 or bigger, then there would be no room left for the third angle, and that would be invalid. So you always have to check to see whether that actually gives you a valid third angle, okay? So those are the two values of beta that I found now, and we're trying to find the length of AB. We're trying to find the length of this side here, okay? And I'm going to use the sine rule again, but with two possible values now. I can write that AB divided by sine of C is equal to BC over sine of A, and BC is 10 and sine of A is 30 degrees, or sine of 30 degrees. And that means I can isolate and I can write AB is equal to, and I should probably, because we haven't seen the unit circle yet, write this as AB is equal to 10 sine of C over sine of 30 degrees. You can check on your calculator that sine of 30 degrees is 1 over 2, and that makes this 20 sine of, and it should be 20 sine of BC over 20 sine of C. Okay, yeah. The step that I forgot to mention is that I found the angle B, but I want to find the angle C because I'm interested in the length AB, which is opposite C, okay? So C is either 180 degrees minus 30 minus 36.9, or that whole thing instead, but with a minus 143. And that gives me the two possible values, 113 or 6.87, okay? Now, if I plug both of those into 20 sine of C, I get the two possible values, 18.4 and 2.39. Explain the fourth step once more. Okay, so I'm not really sure which one the fourth step was, but I'll just explain from maybe after I found the angles, okay? So I found the two angles. Remember, one of them just came out of sine -1 on the calculator. One of them I remembered, oh, hey, I have an obtuse angle as well, so I did 180 minus that, and I found this. And now, let me just maybe simplify this triangle a little bit so that we can see what we're actually trying to find. Yeah, so we have this triangle here, and now I know the two possible values of this angle or this angle. And I'm trying to find the side from B to A, this side here, okay? I can use the sine rule to do that if I know what this angle is, okay? But to find what that angle is, I need to subtract 180 degrees minus this angle minus one of the two possible angles I just found for B. And that it gives me the two possible angles of either 113, so this one is 113, or this one is 6.87. Again, the triangle is not to scale. Okay, those are the two possible angles. And then that gives me two possible values for sine, which I can calculate in a second. But the last step is just to write the sine rule for the side AB opposite C and equate that to BC over its opposite side A. So I write AB over sine C, which is it is this side length here, AB divided by sine of this angle, is equal to this length divided by this angle, sine of that angle, okay? And I know that sine of 30 degrees, you can check on your calculator, is 1 over 2. And so I rearrange this. I bring sine C over here, and I get BC times sine C divided by sine of A. BC is equal to 10. I see that on the diagram. And sine of A is equal to 1 over 2. So it simplifies to 20 sine of C. And then, finally, just plugging in the two possible values in my calculator for the angles that I found for C, I either get 18.4 or 2.39. Okay, let's go over the solution to this. I'm going to draw a picture, because with the sine rule, you should definitely draw a picture with this ambiguous case. And the way I do it is to think about the angle that I'm given, which is the angle at A. So that I'm going to kind of leave on the right-hand side here is the angle at A. Maybe draw that a little bit smaller. I'm going to put A over here, and I'm going to say that that is, we can say that that is B, why not? And that makes that 4. And then I'm going to draw just a long side. I can make it infinitely long, really. I'm going to put the angle of 40 degrees in there. And then I'm going to realize that I have two possible sides of length 3. I have something like this, and I have something like this. So this is how I draw the ambiguous case. It just helps me visualize from the start that there might be two possible angles, okay? And we just got to see whether both of them are valid or not. Okay, so what do I know in this triangle? I know that BC is equal to 3, so that's 3, all right? Let's call, this angle is C. This one is C prime, and this one is C. The acute one, is the one that's less than 90 degrees, is the one that's going to come out of the calculator. So let me set up the sine rule. If I write 3 divided by sine of 40 degrees, write that over the opposite side, that's going to be equal to 4 over sine of C. Rearrange that, and I get sine of C is equal to 4 over 3 sine of 40 degrees. And let me evaluate that with my calculator. 4 divided by 3, and maybe actually, if I share my screen, I'm going to lose the drawing, so I'm not going to do that. 4 over 3 times the sine of 40 degrees is 0.857. And now, if I take the inverse sine of that, I get C is equal to 58 0.98 actually. So it should be 59, but whatever. 59 degrees. I'm just making sure there hasn't been a mistake here. No, it looks fine. 58.9 degrees. All right. That is the first possible angle, and the second angle is 180 minus 58.9 degrees. So if I calculate that, I get 121 degrees. And that angle does fit in the triangle because the largest angle I'm given is 40 degrees. So both 40 plus 121 and 40 plus 58.9 are both smaller than, um, they're both smaller than 180 degrees. So there's no issue at all. Okay? Now, sometimes, let's say I had found that this angle was like 150, if that was what I found, then 150 would be too big to fit in a triangle with another angle of 40 degrees, and therefore I would have to reject it, and I would only have the small angle of 59. Okay? And I rounded the answer incorrectly here, but this is supposed to be actually 59.0. But it doesn't matter. We can tell that it's approximately 58.9 or 121. Okay? Next. Okay, another exam style question. I'm going to give you at least, how much time do we have? Yeah, I'm going to give you 4 minutes to get started. So let's begin. Make a bit of room. What do I know? I know that I can use the sine rule because I have one side and an opposite angle. And therefore I can find this angle up here. So I can write 3 over sine of 40 degrees is equal to 4 over sine of r, or in other words, sine of r is equal to 4 over 3 sine of 40 degrees. And I'm going to type that into my calculator. 4 over 3 times sine of 30. Why did I say sine of 30? Sine of 40. 4 divided by 3 times sine of 40 is, and it is the same as what we got a second ago, 0.857. I'm not even going to bother after that because it's a 0. Okay, so what does that mean? It means that r is equal to the sine -1 of that. If I do that, if I do inverse sine, I get, if I round it correctly this time, it's actually 59.0 because 58.98 rounds to 59.0. 59.0, or 180 degrees minus 59, which is equal to 121. Okay, so those are the two possible angles for r. And I know the side length 4, and I know the side length 3. So I'd like to find this angle here so that I can use half AB sine C. That would be ideal. So let's find the possible angles Q. I'll do 180 minus 40 degrees minus, and then either 59 or 121. And that's going to give me either, I'll double check, 180 minus 40 minus 59 gives me 81 degrees, or if I do the 121, or 19 degrees. Okay, so this is the angle C, or Q actually, Q in this case. And therefore, the area of the triangle is half of A, so 4 times 3 times sine of 81 degrees, or 19 degrees. So I just have to evaluate those 2 times, and this becomes half times 4 is 2, times 3 is 6 sine of 81 degrees, or 99 or 19 degrees. And if I evaluate for 81, sine of 81 is 0.987, so times 6 gives me 5.93. Oops. 5.93, and if I do 19 sine and then multiply that by 6 is equal to 1.95. And someone says, this was actually a really cool question. Oh, thank you. I think I made this one last night. One of the reasons I was delayed this morning, I was making problems late last night, so we had enough stuff to cover today in the session. All right, those are the answers. Okay, so I didn't make a multiple choice. I'm just gonna check with the solution to be 100% sure. Yep, that's what we found. Cool. Next slide. Aha, this is a cool question if you ask me. I have a triangle ABC. I have the side length AB is equal to 3, AC is equal to K, and BC is equal to X. Okay, and the question says, show that x squared minus kx root 3 plus k squared minus 9 is equal to 0. That looks like a bit of a mess, but actually, it's just the cosine rule. Okay, I have the angle 30 degrees, and that means I can write that 3 squared, sorry, the angle 3 squared, which is opposite the 30 degrees, is equal to x squared plus k squared minus 2kx cosine of 30 degrees. And again, we haven't covered the unit circle yet, and we're going to go over more what the specific values of these angles are, but you should know that cosine of 30 degrees is equal to root 3 over 2. And if you don't know that now, come to the session on Friday. We're going to cover that in a lot of detail. But in any case, this becomes 9 is equal to x squared plus k squared minus, and then if I multiply 2 times root 3 over 2, I just get minus kx root 3, okay? And now all I have to do is simplify this to a quadratic. X squared minus kx root 3 plus k squared minus 9 is equal to 0, okay? Now, that is part A. Part B is saying to find the possible values of k. Well, what does that mean, the possible values of k? Well, this triangle, which has a side length x, a side length k, and a side length 3, it exists, okay? It exists because I've drawn it and because I've told you that it exists. And therefore, it must be that x is a real number. I can't have a imaginary or complex number for x. And this is a quadratic in x squared. And I know that it has to have a real solution. When does a quadratic have a real solution? When delta, the discriminant, is greater than or equal to 0. Okay? So this is a funky question where we're combining the discriminant with the cosine rule. But the connection is actually very, very useful because it kind of shows you when you have one possible triangle or two possible triangles, and that actually corresponds to the sine rule at the same time in a hidden way. So if I want to find the possible values of k, then delta has to be bigger than or equal to 0, because when delta is less than 0, I have no real solutions. Okay? And therefore, delta is equal to, in this case, k root 3, or negative k root 3, all squared, minus 4 times 1 times k squared minus 9. I'll just remind you the formula. Delta is b squared minus 4ac. And that's bigger than or equal to 0. If I square this, I get 3k squared. And then there's going to be minus 4k squared plus 36 is greater than or equal to 0. Okay? Which means that 36 minus k squared is greater than or equal to 0, or k squared is less than or equal to 36. I square root both sides, and I get negative 6 less than or equal to k less than or equal to 6. But hang on. K is also the side length, AC, and so it has to be positive. So we must have 0 less than k less than or equal to less than or equal to 6. That is the answer for part B. This is a weird question. I don't know if I've seen something exactly like this on the exam, but it's the kind of trick that they would play on you if they ever discovered this was a thing that they could do. Okay? So 0 less than k less than root 6 is the answer for B. See if I have multiple choice. I do not. Now, given that k is equal to root 27, find the possible values of the angle A. Okay, let's plug in the root of 27. So I get x squared minus, and then root of 27 times the root of 3 is the root of 81. that is being times by x, plus, and then k squared is now 27 minus 9 is equal to 0. And the root of 81 is just 9, so this is x squared minus 9x. 27 minus 9 is 18, is equal to 0. All right, I'm going to use my quadratic formula. X is equal to 9 plus or minus the square root of b squared is 81. And then minus 4 times a times c is 4 times 18. That's 72, so minus 782 all over 2. All right, what does that give me? It gives me 9 plus or minus 81 minus 72 is 9, and the square root of 9 is 3, so 9 plus or minus 3 over 2. 9 minus 3 is 6. 6 over 2 is 3. Or 9 plus 3, 12 over 2 is 6. So those are the possible lengths x, okay? And all we're looking for now is this angle alpha. Okay, so this is x. To do that, I'm going to use the sine rule. How am I going to do that? I'm going to say that x divided by sine of a is equal to 3 over sine of 30 degrees. Sine of 30 degrees is 1 over 2, so I can rewrite this as sine of a is equal to x sine 30 degrees over, sorry, x sine of 30 degrees divided by 3, and sine of 30 degrees is 1 over 2, so it's either 3 times 1 over 2 over 3, which is 1 over 2, or 6 times 1 over 2 over 3 is 1. So those are the possible values of sine of a. And again, we'll cover this more when we talk about the unit circle. I find sine of a is equal to 1 over 2 or 1. Okay, so the sine negative 1 of 1 over 2, you should know this one by heart. That's 30 degrees. And the sine negative 1 of 1 is equal to 90 degrees. Okay? Now you have to remember again with these triangles that you have a potentially obtuse angle, so or 150 degrees if I do 180 minus that. But if I had 150 degrees, it wouldn't fit with this angle of 30 degrees because they would eat up the whole 180 degrees of the triangle. So that's actually not valid. So A is equal to 30 degrees or 90 degrees is the answer. All right, so that's a very tricky question. If there are any questions, I'm going to let you write them out while I clean this up a little bit. We're not going to do a problem here because honestly, I don't think it's that difficult. And it's usually obvious what they're talking about. But you're supposed to know what an angle of elevation is and what an angle of depression is. And this is the sort of classic IB joke about everyone knowing what the angle of depression is. But the angle of elevation is the angle formed if you look up from a horizontal line above your line of sight. So let's say you're on the ocean and you're looking up at a lighthouse. The angle of elevation is basically how far up you have to tilt your head to be looking at the lighthouse. And similarly, the angle of depression is how far down someone on the lighthouse would have to be tilting their head down to see you. And you see that those two angles are actually the same. The angle of elevation is the same as the angle of depression. And that's actually just a rule of parallel lines, that this angle is the same as this angle here. Okay, let's move on. I'm going to give you, 30 seconds to do this example, and we'll continue. All right, let's go over this example. So I have a man who is standing 130 meters from the base of a building, and the building is 45 meters tall. I'm going to draw this out just so we can picture this one time. It's 130 meters from the base of the building, and the building is 45 meters tall. So this is 130 meters, and this is 45 degrees. And he measures the angle of elevation. Sorry, I'm going to draw that as a straight line because that was terrible. He measures the angle of elevation to be theta. And the question says, what is theta to the nearest degree? All right, well, I can't believe I wrote 45 degrees. 45 meters. 45 meters. All right, so I have this angle theta. I have the side opposite it, and I have the side that's adjacent to it. So I'm going to use my tangent. So tan of theta is equal to opposite over adjacent, so 45 over 130. And that's actually not exactly 1 over 3, but it was almost 1 over 3. Maybe I could have picked my numbers better. But that means that theta is equal to tan minus 1 of 45 over 130. And if I do that, 45 divided by 130, tan negative 1 of that is 19.09. So to the nearest degree, 19 degrees. And that is option number 3. One other application that you need to know, and it's not important until it is. It doesn't show up on every exam, but when it does, if you kind of don't know some of the basic rules, you're going to be very stuck. But it's this notion of true bearings, which is essentially the system that we use for navigation on open oceans. So we say that 0, 0, 0 degrees points directly north, 0, 90 degrees points east, 180 points south, and 270 points west. Why do we use this 0, 90 instead of just 90? Because we use these 3 digits to make it clear that we're using bearings relative to north. So 0, 90 tells me that I'm 90 degrees from north. All right. And just using a compass, if that's 90 degrees, then 90 degrees points east, 180 degrees points south, and 270 degrees points west. Obviously, 0 degrees is just north. All right. Now, when you're working with true bearings, it's very important that you actually draw your little compass rose, or at least the arrow north, so that you measure the angles clockwise from the north line. That's how they're defined. So the bearings are defined clockwise from the north. One very useful fact about bearings is that if you want to do a U-turn, if you want to go back in the direction that you came from, well, think about doing a U-turn. That's the same as adding or subtracting 180 degrees. And that's how you would find the direction, the bearing that you would take to reverse something, which is going to be quite common, actually, something that you need to do. And then whether you add or subtract depends on whether the original bearing is bigger or smaller than 180 degrees. So let's say that you're on a bearing of 270 degrees. That's actually just west. Okay, you're going west. And then you do a U-turn. Okay, you do a U-turn, and now you're going to be heading east, which is 90 degrees. Now, if I added 180 degrees, I would get 270 plus 180, which is 450 degrees. Okay, but that's actually the same thing as 90 degrees, because after 360, we've done a full U-turn. We've done a full loop, and we're back at north, and I just add the 90 again. You can also just imagine subtracting 90. Subtracting 180, and that's going to give me 90 degrees. Okay. So let's look at this example. I have a ship leaving the port P at a bearing of 75 degrees. It sails 4 kilometers to the lighthouse L. Then it turns 55 degrees away from north, and then sails to a dolphin watching spot D. Okay, and we want to find the bearing the ship must take to get back to L, the distance that it is from the port when it gets to D, and the bearing the ship must take back to the port. So a lot of things happening here. All right, let's begin. I start at a 75-degree bearing until I get to L, and then I add 55 degrees. That brings me to 130 degrees when I take my 55-degree turn. I sail 3 kilometers to D, and then I do a U-turn, okay? And doing a U-turn means adding 180. So I take a 310-degree bearing. This is 310 degrees to get back to L, all right? And that means that the angle between the north, if I say this is NPL, so this angle here is 75 degrees, that means that this angle here is 180 minus 75 is 105 degrees. That's another property of parallel lines, that if these are parallel, then these angles add up. This is theta and 180 minus theta. Okay, that's 105 degrees. And therefore, the angle PLN, so the angle inside here, is 360 degrees minus 130 degrees minus 105 degrees is 125 degrees. Okay? And now we're going to have to use our cosine rule to find this distance PD. Okay, because we already answered this. This was 310 degrees. Now we're trying to find its distance from the port. So I will do cosine rule. I know that if I call this x here, that x squared is equal to 3 squared plus 4 squared minus 2 times 3 times 4 cosine of PLN, which is 125 degrees. And if you calculate that, you will find that PD, this distance, is 6.23 kilometers. All right. So this is 6.23 kilometers. And now the last question is asking us, well, what bearing does the ship have to take to get back to the port? All right, so I'm going to scroll down. It's going to mess up my diagrams, unfortunately. We're going to use the sine rule now to try and find, because we want to find the bearing back to port. We draw in a different color, is this angle here. And I'm going through this quickly on purpose. I don't want to spend too much time here, but I just want to give you guys some sense of how this works. To find that angle, I'm first going to find this angle. And I'm going to do that using the cosine rule. Sorry, the sine rule. I know that this angle here is 125 degrees, and so I can write 4 over, let's say, sine of d is equal to 6.23 over sine of 125, which means that sine of d is equal to 4 over 6.23 sine of 125. And if I calculate that, 125 sine times 4 divided by 6.23, that gives me 0.526. I do the inverse sine of that, and I get 31.7, so d is equal to 31.7. Notice that there is no obtuse angle here. I can't have 180 minus that, because that would be too big since I have 125 here. So the angle here is 31.7 degrees. All right, and I know that the angle from here to here is 310. So the angle that I'm looking for is 310 minus 31.7, and that should give me my answer, which is, if I scroll down, 278. All right. Okay, let's go over this. We're trying to find, in the first part, the bearing PIL. So not the bearing, the angle PIL, which is this angle here. Okay, I'm going to start by finding this angle by recognizing that I have two parallel lines and I have an angle of 44 degrees here, which means that the angle here is 180 degrees minus 44 degrees, and that is equal to 136 degrees. Okay, and that means that the angle that I'm looking for is 360 degrees minus 136 degrees minus 133 degrees, which is 360 degrees minus 269 degrees. So that's going to give me 91. 91. All right, part B. Find the bearing the ship would take to sail from L back to I. So to get from I to L, it took a bearing of 133. So I just add 180. It does a U-turn. It does 130 degrees plus 180 degrees. And that is going to give me 313 degrees. That's my answer, 313. All right, that was everything I wanted to do for the triangle geometry. We're on to the slightly shorter section now of circle geometry. And this is really, really important because it's going to lead into what we cover on Friday, which is the unit circle and trigonometry and all of that. So this honestly shows up more on the IB than the triangle stuff does. Most of the geometry questions will involve circles or arcs or sectors. So special attention for this section, please. Let's start with what we kind of know from the past, which is that the perimeter of a circle is 2 pi r, or pi times the diameter. And that's actually the definition of pi, is the circumference divided by the diameter is the definition of pi, the original definition of pi, the ratio of the perimeter of a circle to its diameter. And since the diameter is 2 times the radius, the circumference is just 2 pi r. And also, we know that the area of a circle is pi r squared. And just to give you a bit of a sense of what that means, if I were to draw a square with a side length of r, and then I draw a circle inside of this, that didn't work very well, a circle like this, okay, then the area of the square is r squared, and then the area of this circle, you can think of it as the fraction of the total area of the square is pi, okay? So a circle fills up pi fraction of the area of the square that encloses it, and therefore its area is pi r squared. I think it's more interesting to kind of have a visual of like, okay, clearly this circle is occupying, a lot more than half, roughly 3/4 of the circle. Um, and yeah, so maybe that helps a little bit. Okay. And sorry, this is supposed to be 2r. That's my bad. 2r, because the diameter is 2r, which gives 4r squared. Okay. And so if pi is approximately 3, then the area is approximately 3r squared. So a circle has area 8 pi. All right. And I want you to find the circumference of the circle. I'm going to give you 30 seconds. Okay, I think that's enough time. So I have an area of 8 pi, and I know that the area is pi r squared, which means that r squared is equal to 8. Or in other words, r is equal to 2 root of 2. Okay? So if r is 2 root of 2, then the circumference is 2 pi r, which is equal to 4 root 2 pi, and that is option number 1. Okay, this is a kind of critical example that I'm putting forward to introduce the idea of radians. So I'm not going to give you time to do this because I want to give you a good intuition for what radians are actually doing and what they are. So imagine that I have a giant pizza. It's 1 meter in radius. It's a huge pizza. And I'm going to cut it into 12 slices. Okay? I want you to, in part A, find the length of the crust of one pizza slice. All right, so let's first think about the circumference of the whole circle. The circumference of the whole circle is 2 pi r. Or in other words, because the radius is just 1, it's 2 pi, and you can put meters if you want. Okay? So L, which is going to be 1/12 of that because there are 12 slices, is going to be 2 pi over 12 is pi over 6. Okay? And let's think about what the angle theta is, first in degrees and then maybe in radians. So if the whole circle is 360 degrees and theta is 1/12 of that, then theta is equal to 360 degrees divided by 12 is 30 degrees. And here's the key sort of step. Instead of measuring things in degrees, we're going to start measuring things in radians. And what does that mean? Radians are simply going to tell us what the length of the arc traced out by theta is divided by the radius. So in this case, I know that 30 degrees gives me an angle. It's equivalent to the angle of pi over 6, which is the same as the length that I just found. And that happens because the radius is 1. So when you have a circle of radius 1, the arc length is the same as the angle theta. And that's kind of the key idea behind radians, is instead of measuring as a fraction of a total circle, we're going to measure the perimeter scaled by the size of the circle. Because obviously you make the circle bigger, the length is going to get longer. But if I divide by the radius of the circle, I'm going to normalize the measure that I just made. And so if I take the ratio of the length of the sector, the length of the arc divided by the radius, I'm going to get something that is going to uniquely tell me the angle. And in this case, it gives me pi over 6. And so this should show you why 30 degrees corresponds to pi over 6. I hope that connection is helpful. Okay, so the answer to part B is pi over 6. All right, moving on. All right, so now arcs and radians. So an arc is part of the circumference of a circle. It's defined by a radius of r and an angle theta that sweeps out. Hang on, what does it say? Usually paper 1 geometry questions would use radians. Yeah, most often they will use radians. They could use degrees. Radians are also super important because whenever you start having trigonometric functions or identities, we're typically going to be dealing with answers in radians. The question, sometimes it'll say degrees, but usually it'll say solve for x in the range 0 up to x up to 2 pi or something like that. But yeah, mostly paper 1 radians and paper 2 could still have radians, but also will have a lot more degrees. All right, but an arc is defined by a radius and an angle that sweeps out over the circle's perimeter, and that defines this length L. All right, and this doesn't just introduce a new kind of shape, it gives us a new way to measure angles in what we call radians. And the angle theta in radians is the length L divided by r. Okay, so theta is equal to L over r. That's the definition of radians. It's how we come up with these radians. And in particular, you can think about the whole circle when L is equal to 2 pi r. If L is equal to 2 pi r for the full circle, then theta is equal to 2 pi. That's equivalent to 360 degrees. And you can actually think about all the angles in radians as fractions of the total circle, as fractions of 2 pi. Okay? Let's continue. So converting between radians and degrees. Since the perimeter of the full circle is 2 pi r, the angle theta that corresponds to the full circle is 2 pi r divided by r is 360 degrees, which means that pi corresponds to 180 degrees. Okay? So I can convert from radians to degrees by dividing by pi and multiplying by 180. So if I have 0 degrees, that's just 0 radians. 30 degrees, I divide by 180, that's 1 over 6, multiplied by pi gives me pi over 6. 45 over 180 is 1 over 4, so pi over 4. 60 over 180 is 1/3 of 180, so pi over 3, and same 90 is half of 180, so it's pi over 2. Okay, so if I told you to convert the angle 2 radians, 2 degrees, you know that pi radians is 180, so 2 radians is 2 divided by pi times 180 is roughly 115 degrees. So I'm going to give you a chance to do this on your own. I'm going to give you, 30 seconds to convert all of these to degrees. Okay, so let's start with the 7 pi over 6. Okay, so 7 pi over 6 divided by pi is 7 over 6. So I multiply 7 over 6 times 180 degrees because pi corresponds to 180 degrees. And 180 over 6 is 30, so times 7 is 210 degrees. 210 degrees. Now pi over 4 is a quarter of pi, so it's going to be a quarter of 180. That's 45 degrees. Part C, I have 11 pi over 9, so pi is 180 degrees. I divide that by 9, gives me 20, and times 11 gives me 220 degrees. All right, like I said earlier, since theta is defined in radians as the ratio of the arc length divided by r, then I can find the arc length by doing r times the angle in radians. Okay, if the angle is not in radians, you have to convert it to radians first. So look at this example. If I have a circle with radius 4 and an arc with central angle of 55 degrees, the length of the arc is, well, I got to convert 55 degrees to radians by doing 55 divided by 180 times pi gives me 0.96. And the radius is 4, so I multiply by 4, and I get 3.84 centimeters for the length of the arc. So I'm going to give you, I'm going to give you 30 seconds for this. Okay, so I have a circular sector with radius 2 and a perimeter of 6. What is the perimeter of the sector? Well, it's 2 times the radius. It's this, which is 2, plus that, which is 2, plus the arc length. And if that whole thing is 6, then 2 plus 2 plus L is equal to 6. That means L is equal to 2. Okay, so my L is 2, and I know that theta in radians is L over R, and R is 2, so that means theta is just 1. Okay, 1 radian. Oh, sector area. So the sector is the area enclosed between a circular arc and the 2 radii of a circle touching each end of the arc. So if the whole circle has an area of pi r squared and there are 2 pi radians in the circle, then a sector with angle theta in radians represents theta over 2 pi fraction of the full circle. And if that's the fraction of the full circle, then that's the fraction of the area it's going to represent. So I find the area of the sector by multiplying pi over 2 theta times pi r squared, and I get, this formula is in your booklet, it's half of theta r squared. Okay? So I'm going to give you 30 seconds to do this example. I know that the area of a sector, we just said, is half of theta times r squared. And in this case, I have a theta of 5 pi over 6 and a radius of 3. So what does this give me? It gives me 5 pi over 12 times 9, which is 9 is 3 times 3. One of those 3's cancels with the 12. 12 has a factor of 3, so it gives 5 pi over 3 times 3, so 15 pi over 4. Sorry, over 4. That's option number 1. Now time for some exam style questions. For the sake of time, I'm actually going to start straight away because we only have about an hour and 10 left and we still have a good chunk of stuff to do. So I'm going to continue straight away. I have the points P and Q on the circle with center O and radius R such that POQ, that angle there, is 2 radians. And the perimeter of the shaded region is 7 pi. Okay, so this figure has a perimeter of 7 pi. So its perimeter is OP plus OQ plus the arc PQ. I don't know exactly what the best way to draw this. Maybe I'll just kind of put a curly thing like that for the arc. Okay, OP is the radius, and OQ is also the radius, and PQ is an arc. So the arc length is L is equal to theta R. And in this case, I have this angle is 2, which means that this angle on the other side is 2 pi minus 2. Okay, so that means that this is equal to 2 pi minus 2 r, which means that this all becomes 2r from these two r's plus 2 pi minus 2 r. Okay, and if I simplify that, I have 2r here, and then I have minus 2r here, so this just becomes equal to 2 pi r. And the question tells us that this is all equal to 7 pi, which means that r is equal to 7 over 2. That's my radius. Okay, so now I want to find the area of the region inside the circle that is not shaded. So I want to find this area here. And I remember that the area of a sector is half of theta times r squared. And theta is the angle 2, so this is just r squared, which is equal to 49 over 4. Okay, that is my answer. I'm going to check it off and give you guys a chance to type out questions if you have them. 7 over 2 and 49 over 4. I have a circular sector, AOB, so it's a quarter of a circle. This angle here is pi over 2. It's a quarter of a circle. And the radius is 9. Okay? And then I am drawing two circles, two semicircles inside of this quarter circle that are tangent at point X. Right? The first one is centered at M and has a radius which is half of the larger quarter circle's radius. And the second one lies somewhere on C, but we don't know exactly what its radius is. So let's write down what I know. All of this is 9, so all of this must be 4.5. Okay, that's one thing I know. And then let's call this R, and this is R. And because this whole thing is 9, it must be that this part here is 9 minus 2R. Okay, that's just from here to here. That's 9 minus 2R. All right, that's one thing I know. And now that means that I can write this piece here from O to C as 9 minus R. All right. So nothing too tricky so far, but again, the challenge with these types of questions, and this is not an exam style question, by the way, I think it's just good for practicing all the skills that we've been learning, is to kind of be drawing things and figuring out as much as you can bit by bit, okay? I also know that this is 4.5. It's also half of the radius of the larger thing, all right? And now I want to think about this length MC, okay? So I noticed that the length from M to X is also the radius of this smaller circle, which I know is 4.5. And I know that C to X is R. It's also the radius, okay? So the length MC is equal to 4.5 plus R. And now here's the good news. I now have in the triangle MOC, it's a triangle like this, I have this as 4.5 plus R. I have this as 9 minus R, and this is 4.5. And it's a right angle triangle, so what am I going to do? I'm going to use Pythagoras. What does that mean? I'm going to write everything now with fractions instead of decimals, because otherwise squaring is going to be difficult. So 4.5 is 9 over 2 squared plus 9 minus R squared is equal to 9 over 2 plus R squared. Let's expand everything. This is 81 over 4 plus 81 minus 18R plus r squared is equal to 81 over 4 plus 9r plus r squared. Right, r squared cancels on both sides. So does 81 over 4. And I'm left with, I have 9r on the right and negative 18r. So I move everything to one side. 81 is equal to 27r, which means that this r is equal to 3. So now I know that that's 3. All right. And maybe it was worth actually figuring out what the question was asking us for it. But the question is asking us, first part to show that CB is equal to 3. So we've actually done that. That is perfect. We've answered part A. All right. So let's move on to part B. We have done this part A successfully. So I'm just going to check it off. We've done all of this. We used Pythagoras and we solved and we found 3. And now we're trying to find the area of R1, which is this area in here. Okay. And don't despair. I know it looks like a really, really messy area, but I can think about that area as actually if I draw a triangle, and then I have this this sector. God, really stretching my drawing skills. I can just subtract this area, and I'll find the area that's left. Okay, so I found that the base of this triangle was 9 minus r, and I know that r is now 3, so this is equal to 6. And this is 4.5, the height, which means that the area of the right triangle is half of base times side, so half of 6 times 4.5, which is equal to 3 times 4.5, or 13.5. And now, the sectors. What are the angles that we're dealing with? We need to figure out what this angle is and what this angle is. Okay, so let me zoom in on the triangle again that I have. This angle here, let's call that theta. I have and also, by the way, we said that the length of this side was 4.5 plus r, right? Is this calculator or no? Yeah, it's calculator. 4.5 plus r is the length of that. So it means that I can write sine of theta as opposite over hypotenuse, so 4.5 over 4.5 plus r, which is 4.5 plus 3 is 7.5. And I'm going to use my calculator to find what theta is. I'm going to do the inverse sine of 4.5 divided by 7.5. And I will find it's sine -1 of 0.6. And that is equal to 36.9 degrees. 36.9 degrees. All right, and that allows me to find this angle because that's a right angle. So the other angle, let's call that alpha. Alpha is going to be 90 degrees minus theta, which is just going to be 53.1 degrees. Okay, so that is very helpful. Now we know both of those angles, but I actually kind of want to know those in radians. And if I was smart, I would have actually just put the calculator in radian mode, and I would have gotten these angles in radians instead of degrees, because now I have to convert them. So I'm going to do 36.9 divided by 180 times pi, and that's going to give me 0.644. And this one is going to give me 53.1 divided by 180 times pi is equal to 0.927. All right. Now the area of this sector here, well, this is a radius of 4.5 and the angle is 0.927. So its area is half of 0.927 times 4.5 squared. So if I calculate that times 4.5 squared times 0.5, this gives me 9.384. I'm going to keep decimal places for now. And then this sector here has a radius of 3 and an angle of 0.644. So A2 is half of 0.644 times 9, which is, let's do that, 0.6 gives me an area of 2.8958. Okay? And the whole area was supposed to be 13.5. So if I now do 13.5 minus 9.384, 3.84 minus 2.8958. I'm going to get, let me give me a second to type it all out, 9.384 minus 13.5. This is all equal to 1.22. That is my final answer for the area of R1. Okay, so that is part B. Let me erase this and enter that in. 1.22. And now to find the area of R2, it's actually a little bit easier because I know the area of the whole quarter of the circle. Remember, this is a radius of 9, so its area is equal to half theta r squared, and the theta is pi over 2 here, so half pi over 2 times 9 squared is equal to 81 pi over 4. I know that the area of this thing is, let's call that area A, O, I don't know what to name it, so I'm just going to call it A3 because I already used A1 and A2 before. A3 is equal to half of pi r squared, so half of pi times, it's 4.5 squared for that circle. And the last semicircle has half of pi times 3 squared. Okay, so this gives me 9 over 2 squared, 81 over 4, so 81 pi over 8. So it's actually half the area of the larger one, which is an interesting thing to note. And this gives me 9 pi over 2, which over 8 would be 36 pi over 8. All right, and this one is 162 pi over 8. So if I subtract all of those, I get 162 minus 81 minus 36 is 45 pi over 8. And that's the area of R1 and R2 combined, okay? Which means that if I subtract 1.22, I'll find the area of R2. And let's do that. 45 times pi divided by 8 minus 1.22. And I get 16.5. Let's check the answer. 16.5. Okay, I know that was a tricky question. You won't have to solve something like that on your exam, but I think it's a good exercise for practicing all these things and making sure you really understand everything that you need to know about circles and arcs and sectors. Now we're going to talk about 3D geometry. So I should say 3D solids because we're not really going to do geometry in 3D. It's more about knowing the formulas for the volumes and surface areas of certain 3D shapes. So let's start with a sphere, which is just a ball. And you can read its fancy mathematical definition. It's just a perfect ball. And it has a surface area A and volume B, which are given by area is 4 pi r squared, and volume is 4 over 3 pi r cubed. Okay? And I'm going to make a small note here, a side note, because you guys are all in your final revision, which is that if I do dV by dr, if I differentiate the volume with respect to the radius, I'm going to get 4 over 3 pi and then times 3 r squared, which is 4 pi r squared, which is equal to the area. So interesting little note that the derivative of the volume is the area of the sphere. Okay? And I'll let you think about why that might be. Continuing. I want you to find the volume of a sphere with a radius of 3 centimeters. I'm going to give you like 30 seconds to do this. Okay, I think that's enough time. I'm going to use the formula. V is equal to 4 over 3 pi times r cubed. Or in this case, 4 over 3 pi times, and I have 3. 3 cubed is 27. And then I have 27, and I have a 3 in the denominator, so it's just going to be 9. 9 times 4 is 36 pi. Okay? 36 pi is my answer. Centimeters cubed. I have a chocolate ball, and it's being formed by a spherical shell of thickness d. In this, sorry, with a diameter d. The outer diameter is d, and a thickness of 2 millimeters. The shell is filled on the inside with 3 cubic centimeters of caramel, okay? So this ball right now is cut in half just so you can see it, but it's actually a full ball. And I have that the inside, which is full of caramel, has a volume of 3 centimeters cubed, which is going to be equal to 4 over 3 pi times, and the inner radius, let's think about it. If I draw here, the radius from here to here is, well, the radius from here to here, to the outer of the circle, is d over 2. And the only difference here for the inner is the 2 millimeters. So I can do d over 2 minus, and 2 millimeters in centimeters is 0.2. So I can write that the radius of the inside is d over 2 minus 0.2 cubed. All right, and that's supposed to be equal to 3. So what I'm going to do is I'm going to multiply both sides by 3 and divide by 4 pi. So 9 over 4 pi is equal to d over 2 minus 0.2 cubed. And this is a calculator question. We're going to need it. I'm going to do 9 divided by 4 pi. And if I do 9 divided by 4, 9 divided by 4 pi is going to give me 0.7162. Then I'm going to take the cube root of both sides, and that's going to tell me that d over 2 even, d over 2 minus 0.2 is equal to 0.8947. All right, now I add 0.2 to get d over 2 is equal to 1.0947. And then multiply by 2, and I get d is equal to 2.189. So if I round it, 2.19 centimeters. All right, that is part A. Now, hence find the volume of the chocolate shell, not the whole chocolate ball, just the shell, which is the outer part that's made of chocolate. I'm going to think about that as one big sphere minus the inside sphere. And I already know that the inside sphere has a volume of 3 cubic centimeters. So I'm just going to subtract V total minus 3 is going to give me the V shell. All right, and V total is, well, I have a D of 2.19. So V is equal to 4 over 3 pi r cubed, which is 4 over 3 pi times 2.19 over 2 cubed. Let's calculate that. Let's divide the number 2.19 by 2, and then cube it, and then multiply by 4, divide by 3, and multiply by pi. And I would get 5.495. And all I have to do now is subtract 3 to find the V of the shell is 2.495 something. So I have to round up to 2.50. Because if I have 2.495, I round that to 2.410, or sorry, what am I saying? Just 2.50, because the 5 rounds up. Okay. Cylinders. Okay, cylinders are a type of shape that's basically like a pipe. Okay, so you can literally imagine a pipe, and the pipe can either have an open end or a closed end. I'm going to try and zoom out so you can see this a little bit better. And I either have an open end or a closed end, and that's going to impact what its surface area is going to be. Okay, because obviously if I have closed ends, then my surface area is going to include those closed ends. So in the formula booklet, you'll find 2 formulas. You will find that the volume of the cylinder, which doesn't depend on whether it's open or closed, by the way, is just going to be pi r squared h. So you can imagine taking a circle, which has an area of pi r squared, and multiplying it by the height. So you're stretching it through a certain height, and that's going to give you your volume. And then the surface area of the curved part of the cylinder, I'm just going to write next to this, it's equal to pi r squared times h, or area times h. I think that's helpful to understand why. And the curved part of the cylinder is 2 pi rh, which, by the way, is the same thing as the circumference times h, okay? Because the circumference is 2 pi r. So I'm taking that circumference, the circle, and I'm stretching it through a length of h, and that's giving me my surface area. And then if you include the circular ends, both of which have an area of pi r squared, then the total area would be 2 pi r plus h, if I factored out pi r, or 2 pi r. This is not in your formula booklet, but you don't really need to memorize it because you know what the area of the circle is, so you know what the area of the end is, and you have this formula for the area of the curved section. So this is really just kind of like combining both steps together, but you don't need to. Let us do this question. So I have a volume of 36 pi and a curved surface area of 24 pi. So let's remember what I have for my formulas. I have V is equal to pi r squared h. That's equal to 36 pi apparently. And my surface area, the curved part anyways, is 2 pi RH is equal to 24 pi. Okay, let's divide by pi, and I get two equations. R squared h is equal to 36, and 2RH is equal to 24. Now, both of these equations have h in them. So if I actually divide one equation by the other, if I do r squared h over 2RH, the h's are going to cancel, and I'm going to get r over 2, and that's going to give me 36 over 24, which is 3 over 2. And if I multiply both sides by 2, I find the radius is equal to 3. All right. Volume of a prism. Okay, this one is like, it's kind of like the cylinder, to be honest. And this is why I was explaining how we got to that area, that formula for the volume. But if you imagine this weird shape that has it's kind of like star-like base, and I'm just going to generate a 3D shape by stretching it through a height of h. So I'm going to turn it into a prism by lifting it up and creating this shape. Okay, what is the volume of the shape going to be? Well, the volume you can imagine, taking the area of the base and just multiplying it by h. Because imagine, if you will, taking a bunch of tiny slices of paper, each of which are shaped like this, and I stack them all on top of each other. That is how I can get the total volume of the entire thing, by essentially adding up infinitely thin things over a height of h. Okay, and this is actually kind of connected to integration, where I sum infinitely many, infinitely small things to get something that has a finite value. And this actually works as well. If I sum infinitely many, infinitely small slices of this shape, then I can find the volume. Okay? So the formula, which is in your booklet, is just the volume is equal to A times the height, where A is the area of the base. A prism of height 2 centimeters is formed from a right triangle and has two sides of length 3. And we want to find the volume of the prism. And I'm going to say that I have 2 centimeters there. Sorry, 3 centimeters there, 3 centimeters there on my triangle. That means that they are, well, they're not necessarily forming a, oh, sorry, it is a right triangle. What am I saying? And because they're the same, both of them are the same, neither of them is the longest side, which means they are the base and height of the triangle, which means that the area is half of 3 squared is 9 over 2. And the height of my prism is 2, so volume is equal to A times H is equal to 2 times 9 over 2 is just 9. All right, just 9. Right cones. These are a little bit tricky, but they actually show up, I would say, annoyingly often on the IB, and they kind of combine with calculus questions sometimes with related rates, and we'll talk about those next week. But this is what a cone looks like. It's basically this sort of like sharp, circular-ish shape. And in the IB, we only talk about right cones, which means that the peak, the tip of the cone, is directly over the center of the circle, okay? And I believe, though, it actually doesn't matter. If I remember correctly, it doesn't actually matter where the peak lies. The volume is always going to be the same. But still, we only talk about right cones. Okay? So the cone has a circular base. It has a apex or vertex, and it has a height of h, which is from the base to the peak. And then the slant length is L, is the length along the side of this. This is the slant length L. Okay? Now, I think it's worth noting quickly that if I were to draw, I'm going to try and draw in the background, this is where the base would be. So this is the height. And if I draw a radius here, then notice a right angle. And that means that r squared plus h squared is equal to L squared. That's a very important thing to notice. Another important thing to notice in the context of IB is this angle up here, theta, or you can think of this as theta, and then the angle at the top being two times theta, twice the angle that this height, radius, slant length triangle will form. And so there are going to be questions where you're either given or you're trying to find the angle at the apex of the cone using this triangle and trigonometric ratios that like what we've covered today. Okay, let's close that. So yeah, you have the formulas for volume, 1/3 pi r squared h. All right. So again, kind of like I want you to imagine taking a cylinder with the same base and stretching it to the same height. That would have a volume of pi r squared h. So basically, a cone is 1/3 of the volume of the cylinder with the same base and the same height. Okay. So think about if you look at it from the top, all this volume here between the cylinder and this cone part is what we're not counting, and it's actually 1/3, 2/3 is the ratio that they divide each other into. Okay, so the surface area of the cone is pi times r times L. All right, so you take the slant length L, you multiply by pi and by the radius L. Okay, and that gives you the area of the it's this whole surface area up top, the curved part only, not the base, this entire thing that goes around. Okay. And finally, like I said, you have the relationship from Pythagoras that L is equal to r squared plus h squared. Okay. A cone has a volume of 4 pi and a height of 3. And we want to find the area of the curved portion of the cone. And let's remember the formula that I have. It is area is equal to pi RL. So area is equal to pi RL, and volume is 1/3 pi r squared h. Okay, so the volume is 4 pi, which is 1/3 pi r squared times, and the height is 3. So in other words, 4 pi is equal to r squared, or pi r squared, which means that r is equal to the square root of 4 is 2. If I cancel the pi's on both sides, r is equal to 2, which means that this is just 2 pi L. And now I'm going to have to draw a cone over here. Let's draw a little cone with a vertex like that. I could draw a better cone. That was a bad cone. Better cone, a little bit taller. And let's draw the height in here. That's the height. I know the radius is 2. And we also found that the height is 3. So I can write those down. The height is 3. The radius is 2, which means by Pythagoras that L squared is equal to 3 squared plus 2 squared, which is equal to so L is the square root of 13. And I plug that into here, and I get 2 pi root 13. That's option number 4. Now I want to talk about right pyramids. And a right pyramid is a three-dimensional shape whose base is any polygon. So it can be a triangle, it can be a square, it can be a pentagon or an octagon. It doesn't really matter what it is. But its apex is going to be above the center of the base. All right, that's the criteria for it to be a right pyramid. And its volume is going to be 1/3 of the area of the base, which is this kind of, in this case, is a square, but it's not always a square. 1/3 of that times the height. Okay, so what I want to notice here is, imagine that I have a polygon. Let's say I'm doing a hexagon or something like that, and it has a certain area. Okay, and a hexagon has 1, 2, 3, 4, 5, 6 sides. And I want you to imagine that I keep taking these regular hexagon or these regular polygons, but I let the number of sides approach infinity. Now, what happens as I let the number of sides approach infinity is that the shape becomes basically a circle. Okay, the more sides there are, the closer it gets to a circle. And what happens when I have a circle, right? A circle has an area of pi r squared. So if I plug that in here, I get 1/3 times pi r squared h. And that's the formula that we had for the volume of the cone. And that's actually not a coincidence. The shape I would get if I went from square to pentagon, hexagon, and then kept making it more and more sides If this shape at the bottom became a circle, this whole shape would just be a cone. Okay, so you can actually think about the formula for the volume of a cone as a special case of the volume of a pyramid. So a right pyramid has for its base an equilateral triangle of length 3 centimeters. So let me draw that. Of side length 3 centimeters. It's an equilateral triangle, so it's something like this. It's not perfect, but you get the idea. That's 3, that's 3, and that's 3. And it has a height of h. The volume is 9 centimeters cubed. Okay, what's the area of this triangle? So the area is half AB sine of C. All right, so it's equal to half of 3 squared times, and this, in an equilateral triangle, all the angles are 60 degrees because they have to be equal. And the sine of 60 is root 3 over 2, so root 3 over 2. So this is all equal to 9 root 3 over 4. That is the area of my triangle. And the volume is 9 centimeters cubed, and the volume of a pyramid, remember, is 1/3, sorry, 1/3, not 1/2, 1/3 of the area times the height. So if I plug that in, I get 9 is equal to 1 over 3 times 9 root 3 over 4 times h. And if I isolate h, I multiply both sides by, I'll divide both sides by 9 first, so that makes it easier. Then I multiply both sides by 3 and by 4, so that gives me 12 over root 3 is equal to h. And if I rationalize that, that's going to give me 12 root 3 over 3 for h, which is the same as 4 root 3. And that is my answer. All right. So a company is designing a smart pencil with a right conical tip, a cylindrical body, and a hemisphere at its end. So we're going to actually be combining 3 different shapes that we know here. We have a right cone, a cylinder, and then half of a sphere. And we're told that the diameter of the pencil is d, the length of the cylinder is L, and the angle at the tip of the cone is theta. All right? H is the height of the conical tip. So it's this distance here from the conical tip to the base of the cone where the cylinder starts. All right? And in part A, we're trying to show that theta, which is the angle at the tip of the cone, is equal to 2 times the inverse tan of d over 2h. To do that, I want you to think about this diagram of the cone over here. If I draw the height of the cone, dividing the angle into 2 parts, so I have theta over 2, and also the diameter into 2 parts to give a radius, which is d over 2, and I label h as the height of the triangle. And what I can do is realize that compared to the angle theta over 2, d over 2 is the opposite side and h is the adjacent side, which means that tan of theta over 2 is equal to d over 2 divided by h. And then I can rearrange that to say tan of theta over 2 is d over 2h, and therefore that theta over 2 is the inverse tan. If I apply tan negative 1 to both sides, I get the inverse tan of d divided by 2h. And then I finally multiply by 2 to get theta is equal to 2 times tan negative 1 of d over 2h. And that answers part A. Now, in part B, I'm given specific dimensions for the pencil. And what are those dimensions? So I'm told that the diameter is 4 millimeters. The diameter is 8 millimeters. I'm recording, so it's fine. I'm told that the diameter is d is equal to 8 millimeters, which is 0.8 centimeters. And that means that the radius of this whole thing is 0.4 centimeters. That's the radius of the cone and the cylinder and the sphere. Okay? I know that the length of the cylinder is 15 centimeters, and the overall volume is 8.5 centimeters cubed. And this total volume, the 8.5, is equal to half the volume of a sphere, plus volume of a cylinder, plus the volume of a cone. Okay? So let's break it down piece by piece, because we know the equations for the volumes of each of these. I have a sphere with radius r equals 0.4, and therefore its volume is 4 over 3 Let's not forget that I have a half in front. I have half the sphere volume, which is 4 over 3 times pi times 0.4 to the power 3, plus the volume of the cylinder is pi r squared times the length, so pi times 0.4 squared times 15. And then finally, the volume of a right cone is 1/3 pi r squared h. So I'm just going to write r squared is 0.4 squared, and h is still unknown. We haven't been given h. And we need to solve for h, and then we're going to plug that into the formula from A to find theta. All right, so if this is all equal to 8.5, I'm going to write out as much as I can here on the left-hand side. So first thing I'm going to do is I'm going to divide, because every term on the right-hand side has pi in it. So I'm going to write 8.5 over pi. I'm going to divide through by pi, and that's going to give me, then I have 1 over 2 times 4 over 3 is 2 over 3 times 0.4 cubed, plus 15 times 0.4 squared, plus 0.4 squared times h over 3. All right? And now I can turn all of these values into decimals using my calculator. So what I'm going to do is write that h over 3 is equal to 8.5 over pi. Sorry, and this is, don't forget the 0.4 squared here. 8.5 over pi minus 2 over 3 times 0.4 cubed plus 15 times 0.4 squared. And that right-hand side I can evaluate with my calculator. I'm going to do 8.5 divided by pi minus 2 divided by 3 times 0.4 cubed, and then minus 15 times 0.4 squared. Minus 15 times 0.4 squared. This, by the way, made a mistake. It's supposed to be a minus sign. Okay? That gives me 0.2629. And I'll add an extra 7 on there. I'll go to 5 sig figs. Okay, and that's 0.4 squared times h over 3. So if I multiply that by 3 and then divide by 0.4 squared, I will find the height of the pencil. And if I do that, I will find h is equal to 4.93 centimeters. All right. The final step is to plug that into the formula I have from A. So I have theta is equal to 2 times the inverse tan of 0.8 divided by 2 times 4.93. And if I evaluate what is inside the tan first, I do 0.8 divided by 2 times 4.93. Make sure you get your brackets right. You get 0.0811. And then if you take the inverse tan of that, you will find 4.6 degrees. And finally multiply that by 2 to get 9.27 degrees. And the question says to the nearest degree, so we put 9 degrees as our final answer. All right. All right, I'm going to stop the share, and I'm going to give you guys the chance to ask questions. That's everything for today. Ask questions or give feedback about the session or the website or really anything. Just let me know, okay?